My name is Sam Cook, and I will be talking about the Internet of Things. The Internet of Things is a quickly growing network and has numerous applications in smart homes, municipal Wi-Fi systems, smart grids, supply chain management, and health monitoring. The Internet of Things connects ordinary physical objects to one another by using embedded electronics, such as sensors, meters, or anything that can really collect or report information. Anything from a vehicle to your home to streetlights, which are often referred to as things, can be embedded with various electronics for data collection and reporting. Numerous markets and applications of all sizes and complexities can benefit from the Internet of Things. Common applications include smart homes, municipal Wi-Fi networks, smart grids, health monitoring, and supply chain and warehouse organization. In this presentation, I will cover the characteristics, advantages, and enabling technologies for one small-scale and one large-scale application: smart homes and municipal Wi-Fi networks. RFID and optical tags, sensors, and meters are all examples of devices used to collect information and transmit it through networks. A wide variety of devices and technologies make up the network. Basically, any sort of electronic device with network connectivity can be embedded within an object or a thing and become a part of a larger network. A common example are streetlights. Devices such as sensors, cameras, meters, or nodes can be placed atop a streetlight to monitor traffic conditions, provide surveillance for security purposes, or be an element of a municipal Wi-Fi system. A node within a municipal Wi-Fi system can be a data source, meaning that it collects and reports information, or it can be a repeater, which simply forwards information onto the next node. Municipal Wi-Fi systems will be discussed later in this presentation. Now we will consider smart homes. Smart homes are residential houses that take advantage of a small-scale network to connect various appliances, electronics, and systems, all of which can be controlled remotely and automatically. Primarily, appliances, HVAC systems, security systems, and lighting circuits are integrated and automated through use of a control hub and various software. Smart home systems can be highly customizable according to the user's preference. For example, a smartwatch can detect when the user awakes and can transmit a signal to the thermostat to adjust the home's climate to the user's preferences. The system could perform a similar function when the user returns home for the day. Smart homes use low data rate and low power consumption personal area networks to connect sensors, meters, switches, and controllers. Two common network protocols are Zigbee and Z-Wave. While smart homes use small networks to connect various electronics within the home, they can be a part of a larger network like a smart grid or a microgrid. These homes often have small intermittent generation sources such as solar panels or wind turbines, which require metering and reporting capabilities to the utility operator. Numerous companies have designed devices that make up or control smart home systems, which have many benefits for the user. Reduced power consumption and higher efficiency is possible. Sensors and dimmers are used to control lighting used to save energy. For example, occupancy and vacancy sensors are used to sense the presence of someone in a room and can automatically switch the lights on or off. Dimmers control the amount of light used. Coupled with lighting retrofits by installing higher efficiency bulbs, such as LEDs, efficiency can be greatly increased. All systems in the room can be controlled and monitored remotely. The user can check the thermostat settings of their home from work or school via an application on their phone. Climate settings, lighting circuits, and electronic devices can be controlled automatically through programming preferences or remotely from a distance. Accessibility is also greatly improved. For example, if an elderly person injures oneself, this event can be reported to the appropriate service or person almost immediately. Security monitoring is improved with greater integration. A security system can report a break-in to the authorities immediately, or users can monitor their surveillance cameras through software applications. Smart homes are also highly programmable to the user's preferences. Smart homes are designed around the idea of automation. Technologies used are meant to collect information and either respond through a programmed function or report information to the user. Then a control hub sends commands to various systems in the home. Sensors sense light levels, temperature levels, and motion and forward it through the network into the control hub and the user. Smart meters organize and report information for power generation and consumption. In the past, meters provided consumption data in longer intervals and only reported that information to the utility operator. Now, meters monitor power consumption in more frequent intervals and report that information to both the consumer and the utility operator. A primary goal of smart meter design and integration is to provide more information to the consumer so they can monitor and control power consumption more easily. Smart meters can send this information to the personal network within the home, where it's accessible through software applications, and also reports it through a larger network to the utility operator. Finally, control hubs receive information from meters and sensors and route commands to the home's various systems. Smart homes include two common communication protocols, Zigbee and Z-Wave. Zigbee is a protocol based on IEEE 802.15.4. In addition to the medium access control and physical layer provided by the standard IEEE 802.15.4, the Zigbee standard provides security, network, and application support services, as seen in the figure here. The next figure addresses the layer functions of the Zigbee standard. The application layer defines specific functions and entities of the network. The next four layers provide network information including its size, connections, and message encryption. The Zigbee standard is often used in personal area networks for home automation. These networks are a small-scale mesh network where connected devices act as nodes. In mesh networks, nodes either are a data source or a data repeater. Because communications are within the home, transmission ranges between the nodes does not have to be very large. The Zigbee standard is designed for low power consumption devices, which allows for a longer battery life of the various sensors and controls that will be used. Sensors and controls are also low data rate applications, which are accommodated by the Zigbee standard. Z-Wave is another popular standard and is similar to the Zigbee standard. Both the Zigbee and Z-Wave are used in mesh networks and the personal area networks used in home automation. However, there are some key differences. Zigbee uses direct sequence spread spectrum or DSSS modulation. DSSS modulation transmits message signals at a bandwidth larger than the needed bandwidth for the message signal. This method helps prevent interference of the transmitted signal. Conversely, Z-Wave uses frequency shift keyed or FSK modulation. In FSK modulation, digital information is transmitted through changing frequency values of a carrier signal. Once the message is received, it is passed through a circuit which determines the frequency changes and then recovers the original message. Zigbee and Z-Wave also operate in different frequency bands. Zigbee uses the 2.4 GHz ISM frequency band, which is a globally accepted standard. Z-Wave uses country-specific frequency bands, such as the 815 MHz band in the United States and the 868 MHz band in Europe. Zigbee is much more of an open standard than Z-Wave. Many companies design radios which use the Zigbee standard, while Sigma Designs owns the radio system used by Z-Wave. Another application of the Internet of Things is municipal Wi-Fi networks. A municipal Wi-Fi network is a public Wi-Fi system that is deployed over large areas, often in cities, communities, and airports. The network offers free Wi-Fi service to the residents of the community and offers several other benefits to the local government and the community. A municipal Wi-Fi network uses a mesh network which operates by use of nodes dispersed throughout the community. Each node is a short distance away from another one, creating a network of several possible paths for a message to traverse. Because nodes need to be a certain distance away from each other for connectivity to be possible, they are often placed in common objects found in a community, such as phone booths or street lights. Cities in the United States such as New York City, San Jose, and many others have deployed municipal Wi-Fi networks. Cities around the globe have installed similar Wi-Fi networks of all sizes and complexities. In addition to being an accessible and often free Wi-Fi network for residents in a local community, there are several other benefits. Nodes placed throughout a city can be equipped with surveillance cameras. These cameras can be used to monitor traffic and crimes. Also, a widely available Wi-Fi service provides more accessibility to public workers such as inspectors, field technicians, and field engineers. These workers can quickly report status updates and send and receive electrical and water blueprints more easily with a public network. Additionally, the local government will have its network in place and will not need to rely on private owners. Because ownership of the network is simplified, having one owner versus many owners, there are economical and organizational benefits. However, there are some drawbacks to these systems. Security is always an issue with Wi-Fi networks, as encryption is not always completely secure. Having more connections will give more opportunities for problems. These kinds of networks vary in complexity and size and require maintenance. Any outdoor device will be vulnerable to damage due to weather or vandalism. Municipal Wi-Fi networks use mesh networks to provide their service. A mesh network connects nodes together which are embedded into objects around the local community. The node acts as a data source, meaning that it collects data from the surrounding environment and transmits the information to other nodes until it reaches its final destination. The nodes often contain sensors and cameras. Additionally, nodes act as a repeater, which means that it forwards information to the next node. As long as a node is within the suitable distance from another node, they can connect and relay information. So, a mesh network provides network redundancy throughout the system. If one node fails, it can connect with the next nearest node and proceed forwarding information. Mesh networks are self-healing in this sense. While individual nodes must be close together to transmit information, the entire system can have considerable range depending on how many nodes are used and the bounds of the system. Mesh networks employ various algorithms to calculate the shortest distance, node by node, from one point to another. One such algorithm is called shortest path bridging. When one node fails, an algorithm like this computes the new shortest distance. While the Internet of Things has many benefits and applications, there are some concerns and drawbacks. One major issue which we identified earlier while comparing Zigbee and Z-Wave is compatibility among standards. Many standards and communication protocols exist and operate under different circumstances. Competing companies will look to have the most influence on a particular technology by finding ways to control a particular standard. Differing standards and devices make complete integration difficult. The figure illustrates companies competing within different standards. Security and privacy issues will always be present when sensitive information is being transmitted across a network. It is important that the information, like medical records and personal information, isn't transmitted to an unintended recipient. There have been issues in the news of retail stores losing customer financial information to hackers. Large and complex networks open up the chance for problems like these to arise. Lastly, the Internet of Things is extremely complex and is growing in size each year. It's estimated that 50 billion objects will comprise the Internet of Things by 2020. This growing complexity makes it difficult for feasibility and raises questions, as a more complex network requires more maintenance, monitoring, and integration. To conclude, the Internet of Things is quickly growing and offers numerous applications and benefits in smart homes, large-scale Wi-Fi networks, smart grids, supply chain management and warehouse organization, and health monitoring. However, due to the growing complexity of this network, there are issues of security and feasibility.